This before, so this is going to be a very quick overview of shear and bending moment diagrams. I show here a simple beam that spans from the origin on the left side, moves along the x-axis as shown here, y-axis shown there. We have loads applied to the beam, a 200-pound vertically downward directed force 4 inches from the left side of the beam, a 100-pound force 10 inches from the left side of the beam, and the beam length overall is 20 inches. So we're going to use simple statics. We know nothing about the cross-sectional area. We know nothing about the elastic properties of the beam, but we're going to just use statics to calculate the reaction forces R1 and R2, and then we're going to draw shear and bending moment diagrams. So the first thing that we're going to do is we're going to take some of the moments about the origin, and we're going to let that be equal to 0. And I'm going to go ahead and call a counterclockwise moment positive. And so we have that the first moment minus 200 pounds at 4 inches. I have another negative 100 pounds at 10 inches, and I'm going to have R2 out here at 20 inches. The sum of all of those moments has got to be equal to 0. That allows me to solve for R2. That is going to be 200 times 4 inch-pounds plus 100 times 10 inch-pounds, all divided by 20. So R2 would be 800 plus 1,000 divided by 20, which is 1,800 divided by 20, which is going to be 90 pounds. Now, some of the forces being equal to 0, if positive is upward, that means R1 plus R2 has got to be equal to 200 plus 100 pounds. R1 is what we're trying to sort out. So we have 300 minus 90, which gives me 210 pounds for R1. So R1 is 210 pounds and R2 is 90 pounds. I got positive values, so that means the direction that I drew them, positive upward direction, was correct. And what we want to do is draw some shear and bending moment diagrams. So I'm going to take note of the fact that R1 is 210 pounds right here, and I'm going to go ahead and put R2 being equal to 90 pounds over here. And I'm going to use my dashed line to extend down here so I can draw a shear and a bending moment diagram. Right, so now I'm going to go ahead and draw a coordinate system here. I'm going to put my X and Y coordinate system, but I'm going to have my shear stress here, and I'm going to move along the beam along the X-axis. So what do we know? First, most important thing that we have to sort out is what is a positive shear. And so we're going to define a positive shear as a shear that does something like this. That's positive shear. We also define positive bending moment as something that causes the beam to smile. You all know about that. So that's positive moment, and this is positive. So this is positive shear over here. This is positive moment here, and we're going. Okay, so first thing we're going to do is at the end of the beam, we know that we have 210 pounds. So we immediately jump up to 210. That stays the same until we get to 4 inches. Then we have to subtract 200 from it. So we come down by 200, and that leaves us at a magnitude 10 pounds right there. That stays constant until we come to the 100-pound load, and then we drop downward by 100 pounds. Takes us down to minus 90, and then we move across here, and we have 90 pounds at the other end, and we end up at 0. So this is our shear diagram shown here, and it's very important that you close the end of the diagram with this reaction force on the right-hand side. That's how you know you've got the reaction forces correct. The next thing that we want to do is we want to extend that shear diagram to create a moment diagram. That's next on our list here. So I'm going to go ahead and create a moment diagram now. I'm going to put my x-axis in again, and now I'm going to draw the moment as I move across along the length of the beam. So remember, a positive moment is going to cause the thing to smile. Well, the moment is just the integral of the shear. And so what we know is happening is that we start to integrate the area as we move across, the shear area as we move across. And so what we're doing is we're building up area until we have 210 times 4 inches, which is going to be, 840 inch-pounds. Then we start to add more area as we move across. We're going to have this 10 pounds times 6 inches. So we're going to add another 60 inch-pounds to this. It's going to take us up to 900 inch-pounds. And then we're going to start subtracting area as we move to the end of the beam, which is going to look like that. And we could calculate that. What we would do is we have another 10 inches in here. We have a 90-pound magnitude. We're subtracting 90 times 10, 900 inch-pounds. So sure enough, we go from 900 inch-pounds down to 0, and it has to go to 0 because there's no moment applied to the end of the beam. So those are ways of drawing shear and bending moment diagrams, and you can use those because they help you quickly point out where the worst case bending moment is in your beam. So the bending moment, worst case, is 900 inch-pounds. It occurs at 10 inches from the left-hand side of the beam, directly under the 100-pound force load that's applied to the center of the beam. Why do we care about that? We care about it precisely because when we are doing structural analysis on our design components, we want to identify the locations of maximum stress so that we can determine whether or not those locations will lead to failure of the component or the structure.